if you have the electron charge over there, right? So you can have that. And then you can have these three sp2. Right? So oxygen sometimes is going to be sp3, sometimes sp2. Whenever you have the negative charge of the oxygen, always going to be sp2. Okay? So for the delocalization of electron, you must have p orbital there. That means sp2. Alright? So that's why you can see the resonance there. So this is the neutral. Now you have the minus over there. You have minus and plus and oxygen, right? So all those charge separations are because of the pure p orbital electrons. So sigma electron never hop in any position. So sigma bond is always fixed. Electrons are bound. They are not allowed to move anywhere. Whenever you see the negative, positive, resonance, those things, always going to be from the pi electron. Okay? Always from the electron is the pure p orbital, not from the hybrid orbital. So keep that in mind. Okay? So now we're going to see one example of that. So let's see nitrogen, right? So it is pointed over there. So what's going to be the hybridization of the nitrogen there into molecules? So this one, sp2 or sp3? Okay, so 2b sp2 must have pi or minus or plus or radical. Okay? So you don't be confused with that. With any molecule. There's not only nitrogen. Any. Okay? So whenever you have the charge, minus or plus, or radical, one electron, or double bond, that means pi bond, right? If you have those, the atom is going to be sp2, always. Doesn't matter which atom you have there, right? So now, based on that, so see for this nitrogen over here. Do you have any charge? You have a lone pair. It is its own electron. Okay, so it can use to make the bond as nucleophile. It can, but here nitrogen doesn't have any electron from the other atom. Okay, so it is not gaining any electron to have the minus charge. Right? It has not given that electron to any other to have the plus charge. Right? It doesn't have any unpaired electron there. So it does not satisfy those criteria over here, right? So you? Right? Remember, those two electrons are its own lone pair. It doesn't mean that you're going to have minus charge for that two electron. It should have gained the electron from somewhere to have the minus charge. Right? So that means it is not sp2. It is regular sp3. There is no pure p orbital there. Right? But now, this one. So what is going to be? It can be sp3 like this, or it can be other. So you have the resonance structure, right? When you have the pi electron. So what if this go over here or this is going to come here as a plus charge, right? Or what if you're going to use that pi electron to make the double bond over here, right? Double bond. Then it's going to come over here. So you have the minus over here, you have the plus over here. Right? You have the double bond next to that. So actually you're going to have the resonance hybrid for those molecules. You're going to have the electron going here and there from nitrogen to oxygen. Right? So now you can have easily plus over there for the nitrogen. When you have that, it must be sp2. Right? So electron will be empty, pure of nitrogen. So in practice, you're going to have a mixture of sp2 and sp3. So it is possible this should have the sp2 hybridization. Right? So see the difference over there? If you have the charge separation, easy, you get this big sp2 there, or sp, depending on the molecule. So if you don't have that, see whether you have the pi bond next to that. So you have the resonance through that atom. If you have that possibility, it can be sp2 easily. But you don't have any such possibility over here, for the first one. There is no pi bond next to nitrogen, right? See the difference? Good? Alright. So now, physical property, okay, so before acidic property. So now it is obvious, if you consider the previous chapter, so which one going to have the higher boiling temperature, which is going to have the lower boiling temperature, now you know that, right? So the molecule in which you have the hydrogen bonding, dipole, dispersion, all combined over there. If you have that, that's going to have the highest boiling temperature, right? If you have just the dipole and dispersion, it's going to be intermediate, less than the other one. You have the hydrogen bonding, right? And you're going to have more than just the dispersion interaction. So based on that, so now we are dealing with a seed over here, okay? So this is something like this one. So that's the focus. So what do you think? What kind of interaction you're going to have in these molecules? Just the dispersion, right? There is no dipole. There is no hydrogen bonding for this molecule. You have just the dispersion interaction. Correct me if I
No.
So I'm wrong, right?
I
So
hope
you
so.
have obviously dipole because you have the minus over here, you have the plus over here easily, right? So you can have the polarity in the molecule, so you can have the dipole, right? You can have the negative charge to the oxygen next to hydrogen for that easily. Hydrogen can have plus charge, right? So you have multiple possible dipole positions over here, right? And of course, you have the dispersion interaction in that. So now, if you talk about the hydrogen bonding, you have that for alcohol also, right? So for the alcohol, so let me just draw the alcohol. So you have hydrogen bonding for alcohol, right? Like that. So here for the acid, you have that too. So I'm gonna write this way. Oxygen, so you have hydrogen. And now you have oxygen, you have hydrogen, and then you have the carbon, oxygen, like that. So you have hydrogen bonding. So now if you compare with the alcohol, what do you think? You have the more hydrogen bonding or the less hydrogen bonding? Less. So why do you think less hydrogen bonding? Probably this is not right. Because if you compare this value with this value, which has the larger boiling temperature? Acid has large. What that means? That means acid must have more intermolecular reaction than alcohol. Okay? So what's going to be additional interaction you have than that of the alcohol? So you have two centers for the hydrogen bonding. Okay? So here for the alcohol you have only one negative center. So that can make the bond with the hydrogen of the second molecule. That's the hydrogen bond, right? So here how many centers you have? Two. You have double. So one oxygen that has the hydrogen gonna make the hydrogen bonding. It can be a hydrogen donor because that hydrogen gonna make the bond with the other oxygen in other molecule. And then the another part of this one gonna be hydrogen bonding acceptor. Yeah, this is more than the alcohol, right? Or you can say you have the two oxygen center in the acid. You don't have that in the alcohol. So you have more hydrogen bonding interaction in acid than in alcohol. Okay? That's the reason why you have more boiling temperature. So now if you compare with all other compounds, alkane, alkene, alkyne can have the least boiling temperature, right? And then after that, aldehyde ketone can have more than this. Alcohol can have even more than aldehyde ketone. Acid can have even more than alcohol. Right? So that's the trend you're going to have. Okay? So if you have hydrogen bonding in both molecules, both type of molecule, you're going to compare which is stronger hydrogen bonding. Okay? So in this case, I'm not saying that you're going to have only hydrogen bonding in acid. What I'm saying is you have the stronger hydrogen bonding in acid than in alcohol. Okay, so that's the reason why you're going to have more boiling temperature, right? Alright, so if you see the different values within the acid chemistry itself, so all are acid, right? In all these molecules, you have the same functional group there. But the difference is you're going to have different carbon chain length. That means you're going to have the different extent of dispersion force. So the carbon chain is going to have this dispersion force, right? So now, with that, you're going to have the variation in the boiling temperature. Okay? So, of course, larger the interaction, the more going to be the boiling temperature. So you have more and more dispersion interaction when you increase the chain length. So you're going to have the variation in the boiling temperature. So it doesn't mean that all the carboxylic acid are going to have the same boiling temperature. So it depends how large, how long the hydrocarbon chain you have in that acid. Based on that, you have the different boiling temperature. Okay. So also the solubility. So for the lower chain length, it is flexible, completely soluble. So infinite means completely soluble. After that, you're going to have partial soluble. And then, after a certain length, you have the insoluble. Okay? It doesn't mean that all acid is going to be soluble. Some are soluble, some are partially soluble, some are insoluble. Okay? If you have non-polar parts greater than the polar parts, then you can have the partial or no solubility at all. If you have the polar part, which is the carboxylic group part, which is larger than the other one, that is easily soluble. Okay, so that's the point. So in the first few, you have very short length. So in there, the polar part is larger than the non-polar part. You have the molecule, so it is easily soluble. Right? If you go down, you have long chain. So long non-polar part you have in the molecule. So it is virtually insoluble. Right? So that's the solubility. So now if you see the IR spectra, that's the how they say what line you're going to see. So you're going to have the one line for the carbonyl, other line for the alcohol, right? So you're going to see two lines for the shape. So this is that one over here, and then 1700 something is going to be that one, right? So you're going to see both of these two lines if it is carboxylic acid, both carbonyl and hydroxyl, right? So you can easily identify from the IR spectrum and also from the NMR. So you're going to see the different lines, right? So this is SNMR. So you're going to see the hydrogen that is downshifted close to the oxygen, right? That's obvious. If you have the hydrogen away from the carbonyl group or hydrogen, you're going to have the line at lower delta. If you have the hydrogen nearby or next to oxygen, they're going to have the higher delta, that is downshift, right? So down shift means you're going to have the higher delta, right? Upfield shifting going to be lower delta. Right, so don't be confused. Okay. Same as carbon. So the carbonyl carbon in particular, so this carbon, right? That's the one that has the most exposure of oxygen. If you have that carbon, it's going to be way down shifted. So this one has the highest value of delta. Normally it's going to be anywhere from 160 to 200, depending on the environment size of the molecule. Right? So we can easily identify those atoms. So what that means is, if you have carboxylic acid, you're going to have the carbonyl carbon there. That carbonyl carbon has the unique IR line and also unique CNMR line there. Right, so way higher value of delta for CNMR and about 1700 with number for the IR. Right? So we can identify based on the CNMR and SNMR. So for all other C's, if you have at the lower value, that C is going to be the farthest away from the carbonyl carbon. Right? So for example, for this molecule, if I write it differently, all so this carbon is the farthest away from the carbonyl, so that should be the least value of that. Right? All right. Now we're going to see the acidic properties. Okay. So let me give you a very simple example. HCl. Right, this is acid. We all know that, right? So it can easily be ionized to have this when it dissolved in water. Right? So this is proton. So proton S plus, and then this is conjugate acid or base. Conjugate base because they have negatives on there. So you can think the same way for the carboxylic acid. I know it is larger molecule, but you can classify or group in the same fashion. So for this one, this is the carboxylic acid. What you can do is you can just write H plus for that. You can write it. Water plus H plus can be H3O, the same thing. Okay? So this is proton you have. And then this is the conjugate base. Conjugate base. Okay? Like Cl minus base. So now we call carboxylate anion for that, the specific name for that, but it is conjugate base, right? So now all the acids gonna have pKa, right? So this is from Gender 2. So for any acid, you can express the extent of dissociation or the hydrogen ion you have in terms of pKa, right? So pKa is minus log Ka, right? Now what is Ka? So if you write for the acid, say for example this acid, Ka is the acid dissociation constant. So whatever you have ion in the product, over into reactant, right? There's the Ka. Now what do you write for this one? So for this one, you're going to have oxygen, and then you have minus. So take the concentration of that over H3O plus or H plus, whatever you write, same thing, right? Over, what do you have? You have the acid there, OH, that concentration. So water is going to be large, so we can just discard the water. So this is going to be the Ka, right? Now here, the point is, if you have a strong acid, what is going to be the value of Ka? So strong acid means it's going to ionize more, it's like HCl. It's going to ionize almost completely, or you're going to have more ions in the right hand side. Right? That means the strong acid. If you have more H plus, more proton given, that is, the acid is strong, right? If it is a weak acid, then you're going to have less ion on the right side. So you have the unionized molecule more on the left side. That's the weak acid. So that's the reason why we say the strong acid almost completely ionizes when you dissolve it. Weak acid, it does not ionize completely. You have the partial ionization, so you have the equilibrium between non-ionized and ionized ion. Okay? So now, once you know that, so what is going to be the value of pKa for the strong acid? Larger value or smaller value? Smaller, right? So for the strong acid, you're going to have the larger Ka. So for the strong acid, you're gonna have larger Ka. You have the dissociation constant larger, but you have the smaller pKa. Because pKa is a negative log of that value, Ka. So you have this smaller value, right? So that's the reason why in Genchem 2 you compare different acids just based on the pKa value, right? So now if you see over here, so you have the pKa value, this one, this one, this one. So just from the pKa value, so which is going to be the stronger acid? So the stronger one, so smaller one, that's the stronger acid if you compare the other, right? Of course, very, very, very weak acid is base, ammonia is base, right? So that's why you can compare. Similarly, see over here, pKa, pKa, pKa. You have comparable value, but this is the smallest one if you compare that. So this is stronger than these two other acids. Right? So sometimes, depending on the group you have attached to the carbonyl carbon, it's going to modify the strength of acidity and basicity. So whether that substituent part is going to pull the electron away from the carbonyl carbon or it gives electron to the carbonyl carbon, it's going to change the pKa value based on that. Okay, so we're going to see more examples on that. So here, so let's see this part. Okay, so now this is acid. We all know that carboxyl group, right? So you have the carboxyl group there. So in all these, you have carboxyl. So now if you see the pKa value, you have 4.7, 4.8, 1.2, so 2.8, and then you have 0.64. So which is the strongest acid over here? This one, right? The lower the value you have, pKa, that's going to be the stronger. And then higher the value you have, that's going to be weaker. So you have the range of pKa values among these four molecules. But in all these four, you have the same functional group. All are carboxylic acid. Okay? Now, what is the difference? Why you have different acidity in these four molecules? So this is because of the substituent. So what you have attached to the carbonyl carbon. Okay? So here, let's compare with this. You have all hydrogen on the carbon, that is metal, right? So here you have this one unique. And then you have two of these over here. And then you have three of these over here. In all these four molecules, you have carbon next to the carbonyl carbon. But if you see the bond of that carbon, you have different electronegative atoms there. Okay? So, in the first one, you don't have any electronegative atom. In the second, you have one. And then third, you have two of those. And then fourth, you have three of those. So, different fluorine atoms. Right? So now, what's going to be the effect of that? So, effect we're going to call the induction effect. That's the name for that. So, the induction is pulling electrons through the sigma bond you have. Okay? So, do you have any definition over here? Okay. So, pulling electrons through the sigma bond. So, you have the chlorine, you're gonna pull the electron from the carbon, so this is sigma bond, right? You have another sigma bond, so this carbon gonna pull the electron from the other next carbon, so it is a pulling effect. So the chlorine gonna pull electron from the carbon in which it is attached, right? So this carbon over here. And then that carbon gonna pull the electron from the next carbon. And then next carbon gonna pull the electron from the oxygen. And then finally, oxygen is gonna pull the electron from hydrogen more with more force, right? So what's the ultimate result on that? You have less electron on hydrogen, eventually, okay? That means now it's gonna be easier to break if you have the less electron density there. So having electron is making bond, being the bond is stronger. Having less electron is being the bond weaker. Okay? So it is easy to break the hydrogen over here. That's the easier. Okay? Than the other one if you compare. Because on the fourth one you have 3 chlorine pulling electron away from the carbon. So that's gonna impose the greater pull all the way to the oxygen. Right? Now, it's going to be easier to give hydrogen. That is, more ionization of the state. So more Ka. To be more Ka means least pKa. Right? That's the reason why you have the least pKa there. This is called the induction method. Right? So if you have questions like, among these molecules, which acid is going to be the stronger one? So you're going to answer based on that. So you're going to be very careful about the electronegative atom there. If you have the same number of electronegative atoms, see which one is stronger. Right? If you have the same number of electronegative atoms and the same strength, which is closer to the carbonyl carbon? So that way you can answer the question, right? Let's see. So you can answer this over here. So let's see this one, right? So carbonyl carbon, you have that. So next carbon. So how many electronegative atoms you have there? So you have 3 fluorine and then 3 chlorine. So both are at the same distance from the carbonyl carbon. Right? In both molecules you have the same number. But now the question is, which is more electronegative? Chlorine or chlorine? Okay? So less the number of cells you have, more electronegative going to be there because you have the nuclear force more predominant if you have less shielding from the electron cloud, right? That means fluorine is more electronegative. Okay? So then, which one do you choose? This one, right? So both are going to increase the acidity. Doesn't mean that Cl3 is going to make the weaker acid. No, it doesn't mean it's going to make the stronger. But fluorine is going to make liquid more stronger than the fluorine. So that's why you're going to choose the fluorine one. So this is more acidic, right? So another example. This one, right? So again, you're going to see the carbon next to the carbonyl carbon. So this is the carbon you have, right? So now, what substitute you have in that carbon? So in one case, you have the hydroxyl. In the other case, you have the oxygen, right? So it is like having 2 oxygen if you count the single bond at a time, right? So double bond, you have the more engaged than the single bond. So this is going to be a little bit more acidic than this one. Okay, good. So both are as a result of the induction effect. So actually for the first one you have the pi-electron resonance also, additional one. So instead of induction, you have the induction plus resonance for the first one, double bond. You don't have that for the second one. Right? So that's how we're going to answer. So let me go back to this thing here over here. So here, just showing the electron density, whether you have a less or more. Whenever you see the red color over there in the surface, that means more electron density or more electrons and all that. Different cloud, right? So if you have blue, that is the less electron density. Okay? So the point is, if you have more blue on the hydrogen, it's going to be easier to protonate, easier to break the hydrogen, and then it's going to be as ion in the solution. Okay? If you have the more charge separation, like minus and plus, you have the more ions on the right side. That means more Ka. That means least PaA. Right? Or if you want to say the same thing from different, or for the strong acid, you're going to have the more color separation. For the weaker acid, you're going to have less color separation. Right? That's another way of saying that. Same thing. Good? All good? Any question on that? So now, if you have a question like this, then an exam you can answer, right? So this is very frequently asked question. Even in your final exam, questions, you can have question like this. So it doesn't mean that you can have only chlorine there. You can have any electronegative atom there. Okay? So judge the distance, how far it is from the carbonyl carbon, and then the strength of electronegativity, and also the number, how many of those. So based on these three factors, you're going to judge which is going to be the stronger acid. All right. So that now we're going to see the good.
Where the weaker electronegative atom is closer to the acid compared to a stronger one that's farther away.
Yes, you can have that. So sometimes there's going to be like if there is competition, so the question is going to avoid to have the pros. Okay. So say for example, if you have like a two at the same distance, of course you're going to pick this number one. So your question is, what if, let's say you have a acid over here, right? And then you have carbon, and then carbon. Let's say you have the chlorine over there, and then for the other one, like carbon, you have the chlorine, right? Chlorine like that, right? So chlorine is more, chlorine is less, but chlorine is closer than the chlorine. Right? So you have here competition between distance and the strength of electronegativity. Right? So the question going to avoid with those like closeness. So this will be easy to identify. Either this is going to be at the good distance or the different strength of electronegativity or the number, how many, right? So, all right. So now the synthesis. So again, whenever you say the preparation, the reaction is going to be repeated from the previous chapter. Okay. So in the previous chapter, we see the reaction of alcohol. So that one reaction. And then the reaction of carbonyl, this is another one, right? And then this is also ketone carbonyl. So we have that reaction as the reaction of carbonyl and alcohol. So now here the same reaction, it becomes the preparation of acid. Right? Because you have the acid on the right side. So these are the way you can make the acid. Right? So one is you have the oxidation of alcohol. So this is the oxidizing agent. So you're gonna add one more oxygen over here. So this is the oxygen added there from the reactant. So this is oxidation, right? You can make the acid from alcohol. You can also make acid from carbonyl molecule, aldehyde, ketone. So you have different reactants. So you need to memorize reactant. But normally, if you compare the easy way, okay, if you compare reactant with the product, say for example this one. So what is the difference? So the difference is you have more oxygen in the product than in the reactant. So now if you have different choices of the reactant there, reactant, you're gonna pick the one that has oxygen in it. So it's gonna be added to the product. So sometimes this can be very simple, just like common sense, right? So three reactants, you don't have any oxygen there. It is a reducing agent, other like a chloride, something like that. You have only one reactant with the oxygen there, so you don't pick that because you need oxygen to make a product, right? So all oxidizing agent gonna give oxygen, so that you're gonna have more oxygen in the product. Okay? So this is gonna add one more oxygen, so other one more oxygen over here, right? So this one, so you have more oxygen in the product. Okay? That's why we say oxidation, oxygen addition to the alcohol and carbonation. Okay? So the other one, oxidation of alkene. So this is alkene, right? So you have the oxygen in the reactant, oxidizing agent. So you have the hydrate with that, right? And you have the same oxidizing agent, you have the acid. Right? So both are oxidation. So here you have a hydrogen over here, right? So you added oxygen, so this is oxidation. So the same thing over here. You have the hydrogen, so now you have the oxygen. So break over here, and then you have the oxygen. So 1, 2, let me just number that. 1, 2. Those two carbons back. Right? So now the difference is the strength of oxidizing agent. Okay? So if you have the stronger agent, it's gonna go all the way to acid. If it is weaker, it does oxidize, but it's gonna go halfway. So it's gonna be hydrate. Right? That's the difference. So you can go from here to here. That doesn't mean it cannot go. So if you add another oxidizing agent, you're gonna bring to alcohol. You're gonna go there. But if you have the mild or weak oxidizing agent, it cannot oxidize all the way from alkene to acid. You're gonna have the hydrate. So this is the mechanism how it's gonna make the acid, right? So this is alkene, this is oxidizing agent you have. So in intermediate, you're gonna have the bond with the oxygen, right? So carbon 1, carbon 2, carbon 1, carbon 2. You have the oxygen of the oxidizing agent. You have that. And then you're gonna have the bond breaking over there. So you have the double bond with the oxygen. So 1, 2, double bond oxygen. And then you have the hydrate after that, right? OH on that. And finally, you're going to have the double bond. So carbon 1, 2, 1, 2, like that. Right? So, that's the oxidation. So you can also make from alkyne. So this is the type over here, alkyne. Okay. So we know you can have from alkene. You can also from the alkyne, triple bond. So you have the carbon-carbon triple bond over here. So similarly, you can have the hydrate there. So you have the dihydrate, 2 OH groups in the carbon, and you have the acid, right? Finally. So remember, for those oxidation from alkene and alkyne, you must have the stronger oxidizing agent like KMnO4. That's the thing you're gonna remember. If you have the other less strength oxidizing agent, then you can have the alcohol hydrate, right? So that's the compound you're gonna have. Alright, so next is going to be the ozonolysis. Do you remember ozonolysis in Opium 1? You had the alkene reaction. Ozonolysis, what do you do? So for alkene, you're going to just make the molecule hard. You're going to add one oxygen over here, other over here. That's the compound you're going to have, right? So carbonyl molecule. So if you add oxidizing agent with that, so you can have the acid. So one is different than Opium 1. So before you did not have any oxidizing agent. So now you're gonna have the oxidizing agent like hydrogen peroxide. You have that. You did not have this there. That's the difference. Okay? So you're gonna oxidize carbonyl to the acid. So ozone is gonna give the same as this one, carbonyl molecule. And then the peroxide is going to oxidize that to the acid. Okay? One more step. Okay. Nice. Confused? Alright, so make sure you like a review up to this point and ask me.